In this video, we'll embark on a journey into the fascinating world of mathematical modeling and its pivotal role in the realm of control theory. We'll begin by exploring why mathematical modeling is not just an abstract concept, but a vital tool that allows us to gain insights into the behavior of complex systems. As we delve deeper into control theory, you'll come to appreciate how mathematical models help us predict and influence the dynamics of these systems. This video sets the stage for our exploration of this crucial subject. Howdy, I'm just some random nude dude sitting in my closet talking to myself. It's also where I celebrate the power of free thinking and encourage bold ideas. As a society, we're often afraid to challenge the norms and think outside the box. But here, I embrace the unconventional. So sit back, relax, and join me on this journey of exploration, where we embrace our inner nude dude and push boundaries to discover new perspectives. Today we'll embark on a journey into the fascinating world of mathematical modeling, a discipline that forms the bedrock of control theory. Mathematical modeling, in essence, is the art of representing real-world systems using mathematical equations. It serves as a bridge between the abstract world of mathematics and the tangible, complex behavior of dynamic systems. The importance of mathematical modeling cannot be overstated. It enables us to gain a profound insight into the behaviors of intricate systems and, more importantly, empowers us to predict, control, and optimize their actions. Mathematical models are not just academic constructs. They're the foundation upon which we build our understanding of the world. As you delve deeper into control theory, you'll come to appreciate how these models are invaluable tools for engineers, scientists, and decision-makers across various domains. They provide us with the means to navigate the complexities of systems that evolve over time, systems that are governed by intricate cause and effect relationships. In the context of control theory, these models serve as the canvas on which we design and implement control strategies. They allow us to simulate the behavior of systems, assess their stability, and determine how to influence their outcomes. Whether it's optimizing the performance of a robotic system, stabilizing an aircraft in flight, or regulating the temperature in a chemical reactor, mathematical models are the guiding stars that illuminate our path. As we embark on this educational journey, remember that mathematical modeling is not confined to esoteric equations and abstract concepts. Instead, it's a practical skill with profound real-world applications. The series that unfolds before you will demystify this fascinating subject, breaking it down into digestible portions and providing you with the knowledge and tools you need to embark on your own modeling adventures. By the end of this series, you'll not only understand the principles of mathematical modeling, but also possess the ability to apply them to solve real-world problems and take control of dynamic systems. So let's begin our exploration of this vital domain, where mathematics meets the real world. Let's start by demystifying ordinary differential equations, or ODEs, which serve as the foundation of mathematical modeling for dynamic systems. We'll define ODEs and underscore their significance in representing change over time. ODEs are particularly well suited for modeling dynamic systems, which include a wide array of phenomena such as the motion of pendulums, electrical circuits, chemical reactions, and biological processes. Throughout this section, we'll illuminate how ODEs serve as a mathematical language for describing these dynamic behaviors and why they are indispensable. Moreover, we'll delve into the world of practical examples that bring ODEs to life. You'll witness the application of ODEs in scenarios ranging from Newton's second law of motion to the decay of radioactive materials. These examples will demonstrate how ODEs encapsulate the essence of dynamic systems, showcasing their ability to capture real-world phenomena. This discussion aims to bridge the gap between abstract mathematical concepts and their concrete application in various domains. In this section, we'll embark on a comprehensive journey into the world of ordinary differential equations, ODEs, the building blocks of mathematical modeling for dynamic systems. ODEs are, at their core, equations that capture how a system's variables change with respect to time. They play a pivotal role in describing the dynamics of systems that evolve over time, from mechanical systems like pendulums to electrical circuits, chemical reactions, and biological processes. ODEs are the language of change. These equations express the fundamental concept that, in the real world, things change, and they often change in response to the current state of affairs. That is particularly relevant when dealing with dynamic systems, where the values of variables are constantly in flux. Understanding ODEs is essential because they provide a structured way to articulate how these changes occur. The significance of ODEs becomes evident when we consider that almost every natural and engineered system exhibits dynamic behavior. Whether it's the motion of a car, the flow of electrical current, the concentration of substances in a chemical reaction, or the population dynamics of species, ODEs are the mathematical tools that enable us to describe and understand these changes over time. The versatility of ODEs is impressive, as they can be applied to a wide array of systems across various fields. In physics, they describe the motion of objects subjected to forces. In electrical engineering, ODEs explain the flow of electricity through circuits. In chemistry, they capture the evolution of reactants in the products. In biology, ODEs are used to simulate population growth or biochemical processes. This diversity underscores the importance of ODEs as a unifying mathematical language for dynamic systems. To illustrate further, consider the example of a pendulum. Its position varies as it swings back and forth, and ODEs provide a means to describe how this position changes over time. Similarly, in an electrical circuit, the voltage and current evolve in response to various components and inputs. By employing ODEs, we can precisely depict these electrical dynamics. Let's take a closer look at ordinary differential equations in action. ODEs are a fundamental concept in mathematics and science, serving as a bridge between abstract theory and practical applications. By examining specific examples, we can better appreciate the power of ODEs in describing dynamic systems and how they are applied in different fields. One classic example where ODEs come into play is Newton's second law of motion in physics. This law states that a force applied to an object is equal to the rate of change of its momentum. Mathematically, this relationship can be expressed as an ODE, connecting force, mass, and acceleration. This equation provides a quantitative way to understand and predict the motion of objects under the influence of external forces. ODEs, in this context, serve as a bridge between theoretical physics and real-world scenarios, helping us analyze and solve practical problems. In the realm of chemistry, ODEs find application in understanding the decay of radioactive materials. Radioactive substances naturally decay over time, and the rate of decay is directly proportional to the amount of material remaining. This relationship is elegantly captured through an ODE. By using ODEs to model radioactive decay, scientists can gain insights into the decay process and make predictions about the remaining radioactive material at any given time. This has significant implications in fields like nuclear science, medicine, and environmental studies, where precise measurement and predictions are crucial. By dissecting these practical examples, we aim to bridge the gap between abstract mathematical concepts and their tangible applications in various domains. ODEs provide a mathematical framework for understanding dynamic systems, making them an indispensable tool in mathematical modeling and control theory. These equations help us translate complex real-world phenomena into mathematical terms, allowing us to analyze, simulate, and control dynamic systems with precision. Throughout this discussion, it's important to emphasize the central role that ODEs play in understanding and representing the dynamic behavior of systems. Whether in physics, chemistry, engineering, economics, or biology, ODEs are a common language for describing how things change over time. They enable us to create models, make predictions, and develop control strategies. Understanding ODEs and their applications is a foundational skill for anyone delving into the world of mathematical modeling and control theory, providing the tools to solve real-world problems and innovate in diverse fields. In this section, we'll unravel the art and science of constructing mathematical models, which serve as our tools for understanding and predicting the behavior of dynamic systems. Mathematical models are essentially blueprints that help us translate real-world phenomena into mathematical equations. Constructing these models is a structured process that involves identifying system components, defining variables, often referred to as state variables, and establishing the parameters that govern the system's dynamics. Constructing a mathematical model is akin to creating a blueprint for understanding and manipulating dynamic systems. In this section, we'll dissect the anatomy of mathematical models, exploring their essential components, including system elements, state variables, and parameters. Understanding these elements is crucial for crafting accurate and effective models. We'll embark on a step-by-step journey through the modeling process, revealing how they can convert real-world systems into mathematical representations. To make this concept even more tangible, we'll embark on a practical modeling example. Imagine a simple spring mass damper system, a classic example of dynamic behavior. We'll walk through the process of setting up the mathematical model for this system, demonstrating how system components, variables, and parameters come together to represent its dynamics. This exercise serves as a tangible illustration for the modeling process, allowing you to see firsthand how complex systems can be translated in the mathematical frameworks. The outline for this is going to be in the description. To construct a robust mathematical model, we must first identify the core components of the system under consideration. These components can be physical entities such as gears and springs in a mechanical system, or abstract elements like currents and voltage in an electrical circuit. By identifying these elements, we're essentially mapping out the key players in our model. Variables, often called state variables, are the quantities that we want to track and understand in the system. These variables represent the changing aspects of the system, and their values evolve over time. For example, in a mechanical system, the position, velocity, and acceleration of an object might be the state variables. In an electrical circuit, voltage and current values at specific points could be the state variables. State variables are crucial as they encapsulate the system's behavior. Parameters, on the other hand, are constants or values that don't change over time. These parameters dictate how the system behaves but remain constant throughout the system's operation. For example, the mass of an object, spring constants, and dampening coefficients in a mechanical system, or resistance and capacitive values in an electrical circuit, are parameters that impact the system's dynamics. The process of constructing a mathematical model can be broken down into a systematic approach. This outline is going to be in the description. We'll walk through this step-by-step journey to illustrate how a real-world system can be transformed into a mathematical representation. Start by clearly defining the system you want to model. This involves understanding its components and how they interact. Determine the state variables, those quantities that can change with time and are critical to understanding the system's behavior. Identify and quantify the parameters that are fixed and affect the system's behavior. The next step is to formulate the equations that describe how the state variables change concerning time. This often involves expressing how forces, energy, and other factors influence these variables. Specify the initial conditions of the system. These conditions determine the starting values of state variables and are critical for solving the equations. Solve the differential equations you formulated to find the mathematical solution that represents the system's dynamics. By going through this step-by-step process, you'll gain a solid grasp of how to construct a mathematical model for a dynamic system. To make these concepts even more tangible, we'll delve into a practical modeling example using a simple spring mass damper system. This hands-on approach will allow you to see how all the pieces come together and how the process plays out in real-world applications. By the end of this section, you'll not only comprehend the principles of constructing mathematical models, but will also have practical insights into how to translate a physical system into mathematical equations, a skill that is foundational for control theory and problem-solving in various fields. Imagine a car's suspension system, which can be effectively modeled as a spring mass damper system. In this example, we'll walk through the steps of setting up a mathematical model for this system, demonstrating how the system components, variables, and parameters come together to represent its dynamics. These are the system components. The mass of the car's body represents the amount of weight it carries and is represented by m. The spring suspension includes the spring that provides the restoring force when the car encounters bumps or uneven road surfaces and is represented by K. The shock absorber, or damper, controls the rate of oscillation and dampens vibrations in the system and is represented by C. In this model, we'll also consider two primary state variables that change over time. The vertical position of the car's body relative to its equilibrium position. This represents the motion of the car up and down and is represented by x. The velocity is the rate at which the car is moving up or down, indicating the speed of the car's suspension motion and is represented by v. The system components are the parameters, the mass of the car's body, the stiffness of the spring, and the dampening coefficient, which were described earlier. Now let's create the mathematical equations that describe the behavior of the system. Again, this is all in the description so you can see the equations. The force exerted by the spring, Fs, is proportional to the displacement, x, of the spring constant, k. And the dampening force, Fd, is proportional to the velocity, v, and the dampening coefficient, c. Additionally, we have the force due to the car's weight, mg, where g is the acceleration due to gravity. Newton's second law says the sum of forces acting on the car's mass is equal to its acceleration. The spring force is given by Hooke's law. The dampening force is proportional to the velocity, and the force due to gravity is constant. By combining these equations, we can describe how the car's suspension system responds to various road conditions. Solving these equations will provide insights into the car's motion, oscillations, and dampening characteristics. This practical example illustrates how a complex mechanical system, like a car's suspension, may be effectively modeled using mathematical equations. It showcases the application of mathematical modeling to understand and control dynamic behavior in real-world scenarios. Now we'll explore the intricate relationship between a system's behavior and the mathematical models we construct to represent it. Understanding this connection is fundamental to grasping the core concepts of control theory, as it allows us to predict, analyze, and influence a system's dynamics. Mathematical models are more than just mathematical abstractions. They are mirrors reflecting the dynamic nature of the systems they represent. These models capture how a system's variables evolve over time, mirroring the system's real-world behavior. By tweaking the parameters and inputs in the model, we can observe how the system's behavior changes. This dynamic relationship is pivotal in control theory because it empowers us to design and implement control strategies to influence the system's behavior. For instance, imagine a control system for a car's cruise control. The mathematical model of the car's speed and the control system itself interact. By adjusting the control parameters, the model allows the system to maintain a set speed, accelerating or decelerating as necessary. This showcases how the model and system behavior are intrinsically linked to a feedback loop, a central concept in control theory. Dynamic systems can be categorized into different types based on their behavior and the complexity of the mathematical models. Understanding these categories is essential for choosing the appropriate modeling techniques for control strategies. First-order systems are systems that can be described with first-order differential equations. They are relatively simple and often involve a single dynamic state variable. For example, the cooling of a hot object or the charging or discharging of a capacitor in an electrical circuit can be represented as a first-order system. Second-order systems are more complex and involve two dynamic state variables. Examples include the motion of a mass spring system or the swinging of a pendulum. Systems with more than two dynamic state variables are considered higher-order systems. These can be quite complex and might involve multiple interrelated components. Examples range from multi-link robotic arms to complex chemical reactions. Each of these system types exhibits unique mathematical characteristics in their models. First-order systems tend to have exponential behavior. Second-order systems can exhibit oscillations, and higher-order systems introduce more complexity in the terms of dynamics. By understanding these different system types, you'll be better equipped to select the appropriate modeling techniques and control strategies when dealing with dynamic systems in the real world. This knowledge is crucial when it comes to designing effective control systems and making informed decisions to achieve desired system behaviors. This section helps bridge the gap between mathematical abstractions and tangible real-world systems by emphasizing the vital role of mathematical modeling in capturing and understanding system behavior. The feedback loop between system behavior and models is a recurrent theme in control theory, allowing us not only to describe but also to influence the dynamic behavior of systems, making it a powerful and transformative discipline. In this section, we delved into the intricate relationship between a system's behavior and the mathematical models we construct to represent it. Understanding this connection is fundamental to grasping the core concepts of control theory, as it allows us to predict, analyze, and influence a system's dynamics. The power of mathematical modeling extends far beyond theory. It's a practical tool with a myriad of applications in the real world. We'll explore the diverse domains where mathematical models play a pivotal role. From physics and engineering to biology, economics, and environmental science, mathematical models are indispensable for making predictions, optimizing processes, and guiding decision-making. This section will be brimming with real-world examples that highlight the profound impact of mathematical modeling. Whether it's predicting the spread of disease, optimizing industrial processes, or simulating ecological systems, you'll witness how these models solve complex problems and shape our understanding of the world. By the end, you'll appreciate the versatility and broad application of mathematical modeling as a problem-solving tool. Next, we'll explore the immense practicality and real-world applications of mathematical modeling. Mathematical models are not merely theoretical constructs. They're powerful tools with a profound impact across diverse fields, from physics and engineering to biology, economics, and environmental sciences. Mathematical models are ubiquitous in our daily lives, often working behind the scenes to solve complex problems. Consider the design of a modern car, for instance. Before a single prototype is built, mathematical models are used to simulate how the vehicle will perform under various conditions. This includes assessing fuel efficiency, safety, and the comfort of passengers. In the field of civil engineering, models are used to predict how a bridge will withstand loads and environmental stress. These models help ensure the safety and longevity of critical infrastructure. In economics, models are employed to predict market trends and economic impacts. These models guide policy decisions, such as setting interest rates or evaluating the effects of government interventions. In medicine, mathematical models are instrumental in understanding the spread of disease, optimizing drug dosages, and even simulating the behavior of biological systems, from cellular processes to the human circulatory system. One of the core virtues of mathematical models is their problem-solving capability. Whether it's predicting the spread of a contagious disease, optimizing manufacturing processes, or planning for sustainable resource management, mathematical models provide a systematic and quantitative approach to address complex challenges. Consider the field of epidemiology, particularly relevant in today's world. Epidemic models like the SIR, or Susceptible Infectious Recovered model, help public health officials understand the dynamics of disease transmission. By plugging in real data and adjusting parameters, these models allow us to predict the impact of interventions like vaccination and social distancing measures. In manufacturing, models are employed to optimize processes. For instance, a manufacturing plant might use models to determine the most efficient production schedule, minimizing downtime and costs while maximizing output. Environmental scientists use models to simulate complex ecosystems, helping us to understand how climate change affects wildlife, predicts the behavior of ocean currents, and assess the environmental impact of various human activities. These practical applications underscore the versatility and wide-ranging utility of mathematical modeling. The ability to translate real-world complexities in the mathematical frameworks empowers us to tackle problems that might otherwise be insurmountable. I hope you recognize the profound impact of mathematical modeling in shaping our understanding of the world and addressing critical challenges. Mathematical models are not just theoretical concepts. They are transformative problem-solving tools that guide decision-making, inform policy, and contribute to advancements across numerous fields, enriching our lives in countless ways. These practical applications underscore the versatility and wide-ranging utility of mathematical modeling. The ability to translate real-world complexities in the mathematical frameworks empowers us to tackle problems that might otherwise be insurmountable. As we conclude this foundational episode on mathematical modeling, it's essential to reflect on the key takeaways and the exciting journey that lies ahead. We embarked on this educational exploration to unveil the captivating world of mathematical modeling, a discipline that transcends theory and permeates every facet of our lives. Mathematical models, as we've discovered, are not merely abstractions. They are the practical tools that empower us to understand, predict, and control dynamic systems. Throughout this video, we've delved into the core principles that underpin mathematical models. We started by understanding why mathematical modeling is more than just a theoretical exercise. It's a conduit that connects mathematics with the complex, ever-changing dynamics of the real world. By constructing mathematical models, we bridge the gap between abstract concepts and tangible reality. We explored the significance of ordinary differential equations in describing dynamic systems. ODEs serve as the language of change, and they are the cornerstone of mathematical modeling for systems that evolve over time. From the motions of objects to electrical circuits, chemical reactions, and biological processes, ODEs allow us to encapsulate and comprehend the dynamics of diverse phenomena. We unveiled the step-by-step process of creating mathematical models. By identifying system components, state variables, and parameters, we learned how to transform a real-world system into a structured mathematical representation. The practical exercise with the spring mass dampener system illustrated the journey from physical components to mathematical equations. We explored the dynamic interplay between a system's behavior and the mathematical models that represent it. Understanding this connection is pivotal to control theory, as it empowers us to predict, analyze, and influence a system's dynamics. By categorizing systems into first order, second order, or higher order systems, we established a foundation for choosing the appropriate modeling techniques and control strategies. We showcased the real-world impact of mathematical modeling across various domains. Mathematical models are problem-solving tools that inform decision-making, policy, and innovation. From designing cars and bridges to managing epidemics, optimizing manufacturing, and preserving the environment, mathematical models play an integral role in shaping our world and enhancing our lives. As we move forward in this series, remember that the journey has just begun. The knowledge and skills you're acquiring will serve as the building blocks for a deeper exploration into control theory and advanced modeling techniques. Our goal is not only to introduce you to these concepts, but also to empower you with the ability to apply them in the practical problem-solving scenarios. So stay tuned for upcoming videos, where we'll delve into transfer functions, Laplace transforms, and advanced modeling strategies. These tools will enable you to wield the power of mathematical modeling to control and manipulate dynamic systems, bringing theoretical concepts to life and driving real-world innovations. So whether you're an aspiring engineer, scientist, or simply a curious learner, the world of mathematical modeling has much to offer, and together we'll unlock its incredible potential. Thanks for tuning in. I hope you found this video informative and thought-provoking. This is the point at which others tell you, if you enjoyed it, please give it a thumbs up and consider subscribing for more content just like this. But we know that kind of thing is for losers. Don't be a loser. And as always, I welcome your ideas and feedback for future videos in the comments section below. Until next time, keep exploring, keep learning, and keep embracing your inner nude, dude.